Hello, my name is Oliver Labs. I create math sculptures, math objects, math art, interactive math, and other math-related shapes or visualizations via mathematics. And many of my shapes, including those you can see in the image in the back, are based on a single equation. And today I'm going to show you how using mathematical equations can help you to be able to obtain a large variety of shapes you're interested in. The example I'm going to use is the Taiwan national flower, which you can see here, and here I have a larger image taken from Wikipedia. So what's the shape of this beautiful flower? You can see here the stick sticking around, and then it has here 5 nicely curved petals. And today I'm only going to explain you how to create the shape of one of these petals, because then in a 3D modeling software it will be relatively easy for you to combine one of these petals to obtain a whole flower. And the fun thing is you can actually even vary using parameters within the 3D modeler then the shape of each of the petals slightly if you want. So let's have a look at this one of these petals. Here from above you see it's nicely curved, almost like a circle, but then here it changes direction and tends towards almost a thickness of 0, so it gets very narrow here in the middle. Maybe here you can see it again. So it goes from almost 0 thickness, thicker, and then whoop around and down again. So that's the challenge we have. We need to find a shape which looks from above like this, but from the side it's also not just flat, as you can see from the photo here. For example, the petals down here, they're slightly curved downwards. So in order to plane this 3D model for the flower, we need to find a shape which looks from the top like that seen in the photo, and from the side it should be slightly curved downwards. Okay. The tool I'm going to use is called GeoGebra. You can find it freely on the internet on geogebra.org. I use the classic version, so you go to geogebra.org/classic. There you can download it or use it directly on the internet. So here's the interface. On the right side you see a 3D coordinate system now. The standard it would be that it comes up with a 2-dimensional system, but you can change it to a 3-dimensional in the interface. So let's start. I will start with the simplest curve you can come up with, a circle. So that's a circle. And here I have a point on the circle, the blue one. And using a parameter a, I can make the point run around. And I've done this not using a construction, using circle and ruler, but using equations. So what are the equations I used? For the point you see here, the coordinates of the point are 0 and sine a and cosine a. And why does this give a point running on a circle? To make you explain this, let me show these segments. Which change with a point. How is the sine and cosine of an angle defined? the sine and the cosine of an angle. Let's take, for example, here the upper angle. The sine in a rectangle or triangle, the sine of this upper angle is simply the opposite side divided by the longest side edge of the triangle. Okay, but this longest edge is just the radius of our circle, and the radius of our circle, I took it to be 1. So dividing by 1 is easy. We don't have to do anything. So the sine of this upper angle is simply the length of this lower segment, and the cosine is the length of the vertical segment in this visualization. Okay, because the cosine is simply the length of the this shortest of the edge next to the angle divided by the longest edge of the triangle. Okay. So indeed, the coordinates of this blue point are simply in this direction the sine of the upper angle, and in that direction the cosine of the upper angle, and that's what I've done here. Okay. Okay. And to obtain the whole circle, what you have to do, if you remember the angles in the radian system, go here from 0 to 2 pi. So if I want to have the whole circle, then I have to say to use this formula from up here, but for s, I let s run from 0 to 2 pi. Okay. So that's a circle, but we don't want a curve. We want a surface. So what I can do is I take many circles, so not just the fixed circle for coordinate 0, but I can let the first coordinate t vary from 0 to 1.5 to obtain many circles lying next to each other. And I have the circles now, and I can get a bit closer to a petal by not taking the whole circle, but to maybe take half of it, and this looks already much closer to a petal. Yeah, but it should be 0 here, narrow here on one end, get thicker, and then go smoothly downwards again. Okay, so I need to vary the shape of the cylinder in order to be narrow on this side, and then thicker in the middle, and then close here smoothly on the other side. How can we do this? I will model this using equations as well, but I will first show you briefly using just some changes of the equations, how we can model and change the shape of that cylinder by hand. Okay, so either I can for example add a factor of 2 here, and what has happened? Aha, so the cylinder has been stretched in that direction. Or I can go back to 1 and add a factor of 2 here, then what, the cylinder will be stretched in that direction. Okay, so seen from the side, this has changed. Okay, but that's also not what we want. We want something which is extremely narrow here in the middle. So I could maybe scale with a factor of 0.1 for here. Okay, that would be very narrow here, but unfortunately it will be narrow everywhere, so that's not really what we wanted. We want something which gets up and downwards again. So the idea is to not take a fixed factor here, but take a factor depending on that coordinate, and the red coordinate is the corresponds on the value, or depends on the value t. As I said, t runs from 0 to 1.5. That's what I did here, 0t from 0 to 1.5. And yeah, so if I scale with 0 here, then it will be extremely narrow, and in the middle it will be higher if I just not choose a factor of a constant number, but a factor of t. Okay, so the thickness is 0 here and gets greater upwards there. But now, seen from the other side, we're still not 0 in the center. This is clear because we have a fixed factor of 1 here. So let's take t here as well. And then we have the first thing we wanted. It should be narrow on one side. Okay. So, but which function does what we really want? We want to have it narrow on one side, but it should go smoothly upwards and downwards again. And to explain you that, let me first remove all this here and show you how to construct a mathematical curve, which is a little more complicated, of course, than just t. So, for example, I'm going to use this function. Looking from here, you recognize maybe it's just a parabola, and the equation is just t squared, essentially, but I already added a factor of d in here to be able to change the shape. Hopefully you know this from school. Larger values will make the parabola narrower and lower values wider. Okay, so let me take d equals 1. Why not? It's the standard parabola. But I need two more equations. I will also use the cosine equation, and I will use the square root equation. Okay, but it's not just square root of t, it's square root of 3/2 minus t I'm going to use, which has the advantage that it's 0 here where the cosine is 0 as well. Okay, and as you can see, the square root function, the blue one, only goes up to here. It doesn't continue. Why is that? The reason is that for values of t greater or equal to 3/2, so 3/2 is 1.5, so for values of t greater or equal to 1.5, the thing below the square root will be negative, and the square root is not defined for values, for negative values. So that's why the blue function just stops here. It's undefined for greater values of t. Okay. So how can we use this now to create the shapes we want? I will explain you now how this works. What I'm doing actually is to take the product of two of them. So the gray curve, as you can see from the equation here on the left, the gray curve is a factor of m, which is just a fixed number I can vary, times the function called mypo, which is the parabola, and the product with myco, which is the cosine. So the orange one and the purple one, the product of them, how will it look like? It's the gray curve. Why does it look as it does? The parabola is 0 here for t equals 0. The parabola is 0. So the product with the orange number, it doesn't matter which value it has, the product will be 0 because the number, the 0 with multiplied with something is always 0. And the same holds here. The product is 0 because the cosine is 0. And here as well. And here. And there. Okay? So the product is always 0 where the cosine is 0. Okay? And yeah, here the value between these two. The value of the gray function, which is the product, is very low because the purple curve is close to 0. So the product with the orange curve will be something which is close to 0. And here in this region, the purple value is much larger. So the product with the orange one will be yeah, far away from the axis. So that's a nicely curved thing, slightly going up, then going down and upwards again. So for smaller values of the parameter, so I can use parameter m, it almost looks already like the petal seen from the side, which is just slightly curved downwards. So maybe 0.2 or 0.1 or something like that is a reasonable value for this shape. We will see later. To model the view from the other side, I use the same parabola, but now in combination with the square root. So this particular square root is 0 for t equals 1.5, because 1.5 minus 1.5 is 0, and the square root of 0 is 0. And as I already explained, for values larger than t, this is not defined, and for values for lower values of t, it gets upwards here. But the main feature is now it goes down here vertically. So the tangent here is a vertical line, and that's what we need for shaping our view of the petal from the top. Because as you will see, let me take the product of these two now. So that's the product of these two. So the product of these two will go downwards here vertically, and that will just close. Yeah. So in this way, seen from the side, we're able to close the petal at the end. We have a parameter e in this function to vary, making this more extreme or less extreme. Okay. And we can actually even change here the exponent. So we can vary the shape also using this exponent, for example, by choosing 1.2, 1.5. You see, it's not that vertical. It's close to vertical, but not really vertical here. Yeah. Where is it again? I lost it. Ah, it's up here. Or we can almost go to an exponent of 2. Okay. As you like. Okay. Maybe a factor of 1.5, 1.2 is nicest. Choose what you want. Okay. Let me now combine this using our equation of the cylinder. So forget about the original 3 curves. I'll now only use the 2 product curves. And here in the cylinder equation, what I'm doing is to exchange the simple formulas t, which describe this shape here, just from both sides, t here and t there. I replace it by the functions I created. Yeah. So now in this direction we're currently seeing of the shape, it has now exactly, of course, the shape designed using this curve. From the other side, it's still, of course, wrong, because we still have just the value of t here, the factor of t. So I'm going to use here then the other function I prepared to have it look from the other side. Like that. That's exactly how I modeled it. And let's look at it, have a look at it, the 3D shape. Yeah, so this is almost exactly what we wanted already. It is a petal which goes beautifully curved up here and downwards and connects the middle again where it's going to be extremely narrow. So in this way, we were able to use simple functions to create a complex but nicely curved three-dimensional shape we can use as a petal. And the advantage now of having this modeled as a math formula is that it's not only nicely curved, but we have parameters to vary, so we can model tons of different kinds of petals for different flowers, just varying the parameters. Okay. So coming back to what we wanted, here's the flower again. We've realized a shape which looks close to one of those shapes here, using simple math formulas, by combining simple math formulas to yield a little more complex formulas, and giving us free parameters to play with to yield thousands of different kinds of flowers. And combining these petals, we can use symmetry in a 3D modeler and adding sticks and all this to finally yield tons of different flowers, including the Taiwan national flower. So thank you very much for listening. And if you have any questions, feel free to contact me if I have time, and usually I have some time to answer at least briefly. Feel free to ask me questions. Thank you very much.